right, guys. We're getting started. Thank you. Let's quiet down, please. Thank you. And I'm also recording this, so guys, you need to stop talking. Thanks. Appreciate it. All right, so I gave you guys 3 documents. The first document is the syllabus, just like kind of what we're going to cover this semester. Grading wise, everything's the same. You know, like homework is 20%. Haven't done enough quizzes with you guys. I'm going to start doing more of that this semester. I'm going to try to force myself to give you guys more quizzes because we do need that. Of course, test is 60%, final exam 20%. So if we look at the first units, it's going to be a lot of just like closing the loop or tying up some loose ends with Algebra 2 type topics like polynomial rational functions, which we're going to do this unit. The next unit, which we'll get to in February, will be exponential log functions. I figure that one should be pretty short because you guys should be pretty comfortable with that. But polynomial rational functions is going to be a lot of asymptotic behavior, end behavior, things that you guys should be very comfortable with, and we'll revisit when we start doing calculus, because we are going to do calculus this spring. Sequencing series, another topic we'll talk about. Sequencing series, I think it's kind of one of the coolest topics we'll do. There'll be a ski week in between, right? So we'll there's a week off in between 2 and 3. That's going to play a critical role in AP Calculus BC around this time next year, because you're going to be doing some calculus principles with sequencing series. I don't think you guys did that. And do you guys do series or sequences in Algebra 2 trig honors last? No, you didn't. Okay, so that's what you guys did conics, right? Or no? They did. Okay, so probability. That's what it was. Yes, sorry. So this is new stuff, but it'll be good. Then we get to the calculus. Right before Easter break, we'll start doing calculus. So like the A portion of AP Calculus AB, or like the first few months or whatever, probably I say more like the first 2 or 3 months, we're going to cover in this class. So if you want to do AP Calculus AB, and we could talk about your math placement, whatever math class you want to do next year, I will say this: if you guys do AP Calculus AB, you'll be incredibly strong. You won't be bored. I mean, some of this stuff will be repeated, of course. So like the first few weeks, like if you just kind of know, like, I'm going to have a really intense senior year, that's especially the seniors, like you have college apps, maybe you're playing the fall sport, you know, other commitments, maybe that might be again, we can talk later about it, but you will see these topics again. Usually this will be covered in August, 2 limits, and chapter 3 derivatives, broken into 2 parts here. You guys cover sometime early October. Things will feel new once it gets past the fall break. It can be about safety. And AP Calculus BC, which I pretty much think anyone in this class will do. Definitely should push yourself. You don't see you'll just pick up from where you left off. So whoever the AP Calculus BC team, almost likely Ms. York, but I don't know, whoever it is, I will make sure that that person knows that they're worried about things off. They're going to basically pick up the baton to keep going with the new stuff happens. So you can get some calculus for sure, which is kind of exciting because it's a class I've taught many times. And but all of these topics I think are all exciting. So as you can tell, some of the topics we did last semester, like the polar stuff, I liked it, but I'll be honest, I was a little rusty with it. So I kind of made sure we use a lot of graph and calculator stuff. It's still good because you do have to use that in AP Calculus BC. Everything we did has a purpose. You will see these things again. It's not like, okay, you're doing, you're not going to see that ever again. No, you're going to see all this stuff again next year for sure. But this stuff I think is a little more exciting. So anyway, that's the syllabus. Grading is going to stay the same. Let's get to the notes. So notes today should be pretty short. Now, in terms of the homeworks, I'm going to kind of try to pick up the pace a little bit. We don't meet again for 5 days. So we don't meet again until Wednesday. So I'm actually going to assign 2 assignments, 2 homeworks, but you'll have time to do in class. Definitely, I think you can get number 1 done or close to it done, and you'll have a little bit of an extra assignment to do, and then we'll feel kind of caught up at this point. Okay, so let's get to notes. And actually, one other thing I need to pull up. Let me fill out notes here. Give me 1 sec. Just gonna pull on my device, my mobile device. Here we go. Shoot. Hold on a sec, guys. Ah, there it is.
Polynomial.
Give me a sec, guys. Sorry, it's a little slow here.
Okay, like if it's like this, how do I describe it?
Here we go. Okay, we're good now.
Yeah, exactly.
Okay, so we're going to talk about power functions. Guys, quiet, please. A power function takes on this form: y equals k times a to the x power. Sorry, x to the a power. Oh, it's wait, no, it should be the lecture notes. So you guys have three. You guys have two packets, right? There's a homework packet. And there's a lecture notes packet.
What is a polynomial function?
Wait, hold on. Wait. Did I scan the wrong one?
No, I think we have it on like the second part.
Oh, sorry. I'm looking at the homework. Sorry, guys. Sorry, I'm looking at the wrong file. Give me a sec. Hold on. Sorry. Let me. Sorry, I was looking at the homework. My bad. Okay. My bad. Okay, here we go, guys. Sorry. We're in the right place now. All right. Okay. Thank you, Catherine, and everyone else for correcting me on that. Okay. So anyway, we're talking about introduction to polynomial functions of higher degree and power functions. We're going to talk about power functions too. So our goal is to talk about what is a polynomial function. You should be able to answer that. And behavior. What is a power function? How is it different than a polynomial function? Basically, it's going to be where the exponent could be any real number, just so you know. And then general sketches of power functions. Okay, so polynomial, you have some information here on that. N is a non-negative integer, meaning it's a whole number, right? And so x to the n power would be the highest exponent, would be the degree of the function, right? So degree would be n. And you assume that you go in descending order. Sometimes it doesn't necessarily, you skip a term. Like if you have x to the 4 power as your highest exponent, you may not have x to the q power. So be it. The domain is always all real numbers. There are never restrictions for polynomial functions, never a restriction. They're very smooth. They're continuous, means no breaks in them. So just something to think about. And again, they can, do a lot of different things. Like they can be very wavy like this, or a parabola. A parabola is a polynomial function, right? Poly means more than once, more than one term. But even a one-term expression could still be considered a polynomial, like y equals x squared. We still consider it to be a polynomial because it follows the definition, meaning that you have x as your base and the exponent is a whole number. So indicate which of these are polynomial functions. Should be pretty obvious. Only one of them is. Which one is it? C, right. Toy C. It's smooth and continuous. It's continuous on the interval from negative infinity to infinity. It's pretty clear, right? For A, why is A no good? You got a sharp corner. And we're going to revisit sharp corners when we talk about calculus. We talk about differentiability, derivatives. We'll talk about that when the time comes. That's not until the spring, much later in the spring. How about why is B no good? Yeah, not continuous. There's a break there. Even though the domain's all real numbers, but still it's not continuous. And how about D? Yeah, it would be. Yeah, it's definitely not continuous. At x equals 0. And in fact, 0 is not part of the domain, right? So that's also an issue because you have to have all real numbers. So we're getting kind of a little more granular. Excuse me, granular with the definition. So choking out that donut I had about 20 minutes ago. Sorry, I'm still enjoying it. Okay, it's delicious. All right, okay, no, it's random. Okay, I shouldn't be eating donuts. It's not good for you, but anyway, this is there. Had to have one. All right, end behavior. Okay, end behavior is looking at the ends of the graph. Okay, end behavior is a huge deal, especially when we get to rational functions, which we are going to do in this unit. Horizontal asymptotes, we talk about that. There's a lot of misconception about horizontal asymptotes, like, oh, it's a region you can't cross. Not true at all. Rational functions can cross horizontal asymptotes. It's all about end behavior. For now, we're not talking about asymptotes because we're talking about polynomial functions. So end behavior is just how the ends behave. That's all that's happening. So you got to think of it like a limit. Now, did you guys ever use limit notation in algebra 2? Did Ms. Wong teach that to you guys? She did or did not? It's really simple. Okay, she did as, right? Okay, it's the same thing. So let me actually okay, so you would see something like this, right? In algebra 2 trig honors. You can write this more concisely like this. So nothing wrong with this. In fact, actually, I don't know if which one's shorter, maybe probably about the same amount of writing. But this is the norm, just so you know. LIM is short for limit. X arrow negative means x approaching infinity. F of x means you're taking the limit of f of x. You want to know what is y approached as x approaching infinity. So in layman's term, because sometimes it just seems like Greek, and actually we do use Greek alphabet sometimes in math, but it does seem like it's kind of cryptic. But in layman's terms, what this really means is what does y approach as x approaches negative infinity? That's what that means. But that's a lot of words. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a lot. More compact here. That's what we have mathematical notation to express what we want in a more efficient manner, right? So that's what it means. Get used to it because you're going to see this a lot this semester, and you see it daily in calculus. Every day you see this kind of stuff. Just gotta get used to it. So yeah, that's all it means. And then of course, if I switch it up, if I turn it to a positive infinity, if I do that, then guess what? I'm gonna write positive infinity. That's all. So this is gonna be the left end, and that's gonna be the right end. Just so you know. And then looking at the annotated notes, yeah, so graphically speaking, we're looking at the far left and the far right. So you want to get political, ultra liberals, ultra conservatives. And I'll hold back because I have strong feelings about both sides because I'm more of a moderate. But anyway, it's not, we won't get into politics. I mean, that's actually more entertaining to talk about than this stuff, but that's okay. Plus, I want to keep my job. So, yeah, I feel bad for the history teachers for next fall. I feel really bad for them. Yeah, no, we're bracing ourselves because we were closed in 2020. 2016, we actually have some stories if you guys want to hear stories. But actually, the date the day Trump was elected, it was actually my son was born, so I was not here, but it was crazy here. So, but when I finish, because I should teach math. Okay, but anyway, it's going to be a contentious time, so let's keep moving. All right, yeah, okay. I know you guys are talking about let's. All right, yeah. Anyway, part A. So here we got x cubed, right? Minus 2x squared minus x cubed. Here's the deal. Both of these have the same end behavior. They're gonna have the same end behavior. Because all that matters is the leading term. All that matters is the leading term. So your leading term is gonna be an times x to the n power, right? That's an a, sorry. Okay, now that just looks sloppy. Let's see here. A sub n. So that's going to be your leading coefficient, right? And that's going to be your degree. And it's really just two things you have to look at for each of those. Is the leading coefficient positive or negative? Is the degree odd or even? That's it. That's all we care about. So do a little quick table here. A sub n and n, positive, positive, negative, negative, even, odd, even, odd. If you have this case, both up. If you have this case, it's like this. You have this case, it's like that. You have this case, it's like that. And I'll call this end behavior. Even though you should be writing limit notation, but just show the arrows. So that's all you're doing. That's it. And you guys should know this from last year. So in the case here, clearly I'm odd and positive, right? Positive and odd. So yeah, I expect the arrows to go up, then sorry, down, then up. And graphically speaking, it's probably gonna look something kind of like this. Of course, they're different graphs, right? Because this one would have a bunch of x's. So that's not about. But the bottom line is this, that your leading coefficient is positive, your degree is odd. So think about what if x gets really big, right? Just think numerically. What if x gets really big? Who cares if it's 2x squared negative x? The x cubed dominates. The leading term always dominates minus x1, right? So if I put in 100, that becomes a million. That's 20,000, big deal. A million much bigger than 20,000. So overall, y gets bigger when x gets bigger. But when x is negative, you're raising a negative number to an odd exponent, it's negative. Right? Who cares if that's positive or whatever? Doesn't matter. That dominates, right? Then of course you have x cubed, it's still going to follow whatever x cubed. So when x is going to the left, or x is negative, y is going towards negative infinity. So that's what's happening with that one. So the other one should be pretty straightforward. Clearly you're negative and odd here. We're positive and even here. So I expect the reverse here. Positive infinity, negative infinity, positive infinity, negative infinity. Both positive infinities here. Does that make sense what I'm doing so far? Yep. Should be hopefully review. Okay. Can I move the screen? Are we okay? Or you guys still jotting stuff down? All right. And actually I could do this. That helps. Okay. And for the last one, part D, That's gonna be negative and even. So it's negative infinity all over the place. Because y is just gonna be going down as x gets bigger or smaller. Doesn't matter. So what you notice, summarize in the box to the right of each part. I already did the summary for you, that table there. That table is your summary, right? I already did that for you guys. Okay, we're good. Okay, let's move on to the next page. Again, these notes are pretty short, so we should be done fairly soon. Yeah, I think this is just kind of repeating what I just said. So a to the n is a leading coefficient. N's a degree. And again, this is just if n is even. Yeah, hold on a sec. Because I do want to write the limit notation here. That's supposed to be a less than symbol. My apologies. So you're going to be writing this, the limit as x approaches negative infinity of f of x equals. You know what? I already did it for you guys. We're just repeating our efforts. If you want to write the limit notation, I'm just going to say this, guys. I already said it already. It's going to be up, up, down, 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 up, up, down. You guys know the limit notation. I already did on the previous page, so we don't have to do it again. So that should all make sense. So I don't, yeah. Okay, we're good on polynomials then? No problems? Okay. And by the way, x-intercepts, you know, well, a lot is going to require some factoring. We'll get that. We'll talk about that a little later, maybe next week sometime. I got to look at the notes. So that's not hard, but we do have to talk about when a graph bounces off the x-axis and doing sign charts. We'll have to have that conversation. Super.
Last year for polynomial division, we learned the box method, but I'm stressed with that division style.
Oh, you mean like synthetic? Oh, to solve? Yeah. Yeah, it just depends on. Well, first of all, I mean, you should use synthetic division whenever you can, because it's way more efficient than long division. So, like for example, if I were to give you like an x-intercept that's already on the graph, but the other zeros are imaginary, then of course what you do is you do synthetic division with what you know, break down the polynomial, and then continue breaking it down with other things you might know about the function. But if I'm asking it to divide, when we get to rational functions, right? When we get to rational functions, then we have to find like slant asymptotes. You guys do slant asymptotes? Yeah. If the denominator is a simple binomial of the form x minus something, like we just have x minus a simple plain old x, yeah, do synthetic. But unfortunately, if the bottom is like a quadratic or it's something really wacky like 4x plus 5, definitely if it's not linear, you're going to have to use long division. If it's linear but has a coefficient that's not 1, you can kind of pull out that coefficient, but you should always try to do synthetic if you can. Because long division is just more steps, so you're more likely to make an error. But we still have to be adept with it because sometimes you have no choice but to use it. Especially in AP calculus, there'll be times where you have to use both. In some calculus problems you do. So it does come back for sure. Anyway, power functions. Move on, guys. Okay, power functions is a big deal, especially in calculus. Guys, quiet, please. So K and A are non-zero real constants, okay? Non-zero real constants, okay? And it can't be 0, right? Because what if K is 0? Then you just got Y equals 0, right? That's lame. Or what if you have this here? K times x to the 0 power. What's x to the 0 power? So it's just a horizontal line, right? That's kind of lame too. So you gotta make sure it's not 0. Now for power functions, and I think this is actually really cool. I really like this stuff a lot. Let's do a little comparison between the two. And then we'll get into power function in a little more detail on the next page. But we're going to do kind of a comparison between these two functions, polynomial and power. Okay, so a polynomial function has one or more terms, which is kind of a misnomer because poly means more than one, but that's right. Power terms will only be one term, or power functions only one term. Okay, only one term. The coefficients are all real numbers. Where the coefficient here has to be a non-zero real number. Your powers have to be whole numbers. Your powers here can be actually anything except zero, because then it would just be a horizontal function. So I'll give you some examples in just a sec. And sometimes it could be both. So here are some examples. And switch colors. Like y equals x squared, right? Plus x plus 1. That's a polynomial function. That's not a power function. Or y equals, let's say, 2 times x to the 5th power. Okay, that's a polynomial still. Now over here, so you're going to x to the 3/2 power. That's a power function. That cannot be a polynomial. That cannot be a polynomial. Y equals 2 times x to the 5th power. That's still a power function. You have one term. The exponent is fine. It's not a problem. That can still be considered a power function. So power function is just one term, x raised to some power. Not exponential function, mind you. Exponential function is when it's a base, a constant raised to x. X is our base here. But polynomial has to have more than one term and only a whole number of exponents. Where power functions could have any kind of exponent, as long as it's not zero. Okay. So let's keep moving. Yeah, good. Yeah, it's just y equals 5. Yep. Yep. So consider a polynomial. It's a horizontal function, but yeah, or a constant function. Okay, so sketching the graphs of power functions by hand. So usually what we do is you look at the first or fourth quadrant, and then you have to kind of ask yourself about even odd behavior, or whether the coefficient is positive or negative. Like you have to kind of do a little more analysis to get the rest of it. But usually we focus on the first or fourth quadrants when we draw power functions. So let's look at this here. There are 3 types. The first one, I mean, I guess it could work. We just don't look at it. That's just y equals x. I mean, you know how that looks, right? That's just that. Right? Y equals x. Easy peasy. But y equals x squared looks like that. And by the way, I'm only going to focus on the first quadrant right now. So let me actually erase part of this line just so it's to avoid some confusion. So y equals x squared. Okay. The next one's y equals x to negative 1. You guys should know how that looks. That's a rational function. or 1 over x, right? You should know how that looks. And then this one here is like a square root function, right? Or root x. So there's really 3 cases. I don't care about y equals x. There's really only 3 cases that we really care about. All of them will pass, and I kind of didn't do this accurately, but all of them should pass 1, 1. Yeah, I didn't quite do this accurately, so my apologies. But all of them should pass 1, 1.
You did it.
Thanks. Well, I appreciate it. Okay. Let's like the vote of confidence. All right. Now, when k is positive, right? When the leading and by the way, the categories are this. In case I forgot to mention, the categories are a is less than 0, a is between 0 and 1, or a is bigger than 1. I don't really care about a equals 1, but I'll just write it down. But I don't care about a equals 1. So really, it's a curvature, right? Because when a is larger than 1, it's going to increase kind of quickly, right? You expect that to happen. If a is between 0 and 1, it's going to increase, but not as much, right? Like a rapid function. So you kind of like this ground curve. If a is less than 1, it's going to be like a reciprocal function, right? It's going to be decreasing as x gets bigger, right? So you draw it like that. And again, I don't care about the green line. So again, if k is bigger than 0, you're going to be in the first quadrant. And yeah, so generally speaking, the shapes will be like this. It'll be like that. It'll be like that. Or it'll be like that. Those are the shapes you would expect for power functions, depending on what a is, what category is. And of course, if k is less than 0, you can be in Q4. Remember, that's your coefficient. That's what k represents. Now, sometimes they might fall in the second or third quadrants. Depends on domain. And even / odd behavior. Do you guys remember even functions? How are even functions symmetric? They're symmetric about what? Even functions symmetric about the y-axis. How about odd functions symmetric about what? No, the origin. Yeah, you think of inverse functions. Y equals x. So we'll talk about that in the examples that are coming up. All right, then for part B, again, so you have 4 categories again, right? A is less than 0, a is between 0 and 1, a equals 1, a is bigger than 1. In this case, k equals 2. So negative 2x, that's pretty easy. Looks like that. Go red again for this one here. That's going to be like this. Right, because we have negative coefficient. Wait, I messed up. Sorry, guys. It's supposed to be like that. Yeah, what's up? Just so you can generalize it. That's why. And then you make an adjustment depending on what's even, odd, or domain. Then you figure out the other parts depending on what your domain is. And yeah. And I'm going to do some of the homework for you guys so you guys can see how this looks. Then lastly, this one here, I meant to do this. I kind of messed up, but all supposed to here in a second, -1, -2. So my apologies. I kind of messed that up. So You're right. 1, -2. You're right. And again, this depends on domain and even odd behavior. Okay. And you do have to be very well versed in determining the curvature for these, because you're going to be applying calculus principles actually in a few months in this class. We will be doing that. So you have to kind of have this image of how these look. All right. So let me pull up this. You guys don't have this document, but this is something I used to give to my students when I taught AP Calculus AB. It's funny how I just remember that. No, that's not the one. Gosh darn it. Hold on. Power functions. There we go. That's it.
You keep like all your old documents.
Oh, yeah. It's all in Dropbox. It's all in the cloud. But then the Dropbox is connected to my hard drive. That's how I could just do. That's how I could. It will manage everything because it's just too much otherwise. Okay, so let's take a look at these here. So you're asked to graph these, right? So start with the first quadrant or the fourth quadrant if there's a negative coefficient. Actually, none of these will have anything in the fourth quadrant because I kept all the coefficients 1 here. So x to the 1/3. That curvature has to look like this. You guys don't have this, by the way. I'm just doing this for you guys. Just that would have to look like this, right? 2 is going to do the same thing, right? But look at 3. Look at 5 and 6. Why am I doing that? Greater than 1. Now, let's do the other side. Let's do the left side of the y-axis. If you're cube rooting, can you plug in negative numbers if you're cube rooting? Yeah, totally. Yeah, and it's an odd function. Because guess what? If I plug in -1, I get negative outputs, right? If I plug in 1, I get 1. Plug in -1, I get -1. So it's going to look like this. That's how it will look. Now let's look at number 2. What do you think number 2 is going to look like on the left side? No. It's an even function, guys. Why is it an even function?
Oh, because it'll be positive when you mix it up.
Look at that numerator. That's an even number. The domain's all real. You can fit through whatever you want. I don't care. So that's an even exponent, guys. That's an even function.
That's an odd function. That's an even function. So you got to pay really close attention to both numerator and denominator of the exponents. Now let's look at 5. Is that all real numbers? Yep.
If the denominator
Is even?
also even.
Forget it. Then you can't do left side.
Okay.
Like in the case. So, oops, sorry. So this would look like this. 6. You're done. Because the domain. Your domain's that.
That's why you do that one.
Let's look at some more here. Yeah, this is kind of, so we always do this at the start of AP Calculus AB because we need to make sure students are comfortable with how these will look. Like for 3, okay, I could do this. And what would the left side look like, guys?
What's function again? It's the big.
Oh, big back up.
Oh, show number 6. Oh, so it goes back up. So I didn't want to be back up. Sorry, I misunderstood you. It's a dual. Audie, do you have a question about what was the question? That's where you can't do something to the left of the y-axis. Is that what you're asking about, or?
No.
Okay. Okay, let's look at 4, guys. 4 looks like this. Can I do anything to the left for number 4? No, because you have an even, right? Even denominator. This one's going to look like this. And what would it look like this side, guys? Would it be like this? No, because your exponent is even for the numerator. It always stays positive. Yep. Here, you'd be like that. You could plug in negative numbers, okay, but it'll be negative. That's an odd function for number 8. 3 is an even function, 7 is an even function also.
So you could just test by plugging in numbers.
Totally, 100%. Yeah. Think numerically for sure. Yeah. Okay. So I'm all done. You guys have about a half hour to get started on homework. So homework is this right here. A lot of it's just like old school stuff. To see how it goes. I have the answer key for this as well. And then also homework 2, I'm gonna have you do as well. And that's just kind of what we just started talking about today. Should go by, if you guys want to start with that one, you can. It's up to you. Homeworks in 1 and 2. Yep. 1 and 2. Yeah. But I'm not gonna get the 5 days, so I don't feel as bad. Signing. Yeah, Andy, go ahead. Yeah. Mhm. Denominators of, because you can't fourth root negative numbers. It's a fourth root. Yeah, raised to the 5 horsepower. Your denominator is an even number.
Oh.
You can't even root negatives. That's why. This is gonna be the right side. Yeah. Yeah, you just have to, it's every situation is unique. You have to kind of treat it like that. So you guys do your homework 1 and 2. Schoology is not